Is the audio working? La la la. Yeah. Come on, get. All right. I will begin with a word of prayer once I get up here. So, dear Heavenly Father, we thank you again for your many blessings and opportunity we have just to study your creation this day. Again, I pray that you be glorified in what we do and that we all understand a little bit more about linear algebra together today, Lord. In your name I pray, Lord Jesus. Amen. So, I have good news and the bad news. The good news is that this is not on your test, but the bad news is also that this is not on your test, because what we're covering today is pretty easy. So, today we're in section 6.1, which is on inner products and norms. Yeah, I will test on this material eventually. So here's the definition. An inner product space which I think I'm going to call an IPS because I get tired of writing inner product space every time here, is a vector space V over K, a field, paired with mapping, which we'll use this notation for. V.
Why are you using K instead of F?
Oh.
Felt like it?
Felt like it, yeah. Such that axiom A, x plus y, a less glib answer to you is I use K when I'm primarily. I don't know. Anyway, when I'm mostly thinking of the field either being the reals or the complexes. And it'll become clear why I'm doing that in a second here. So it's additive in the first slot. And we can pull constants out of the first slot here. And the complex conjugate is, it flips the order like this. And then D, if x is not equal to 0, then the inner product of x with x is an element of 0 to infinity. All right. So, when I write K, I have primarily in mind either the reals or the complexes. And so, what's the complex conjugate in the real number system? Like, what do we do there?
Just the complex conjugate of x is x?
Complex, exactly. So, like, this should be understood if K is equal to R or some other subfield which is real, then the complex conjugate is just equal to the thing again, and that's equal to yx. So this property is called symmetry. All right. In fact, truth be told here, if we're working over the real field, I could say that inner product is a symmetric bilinear form. Well, yeah. Is a symmetric bilinear form. All right. It's more than that, though, because it also has this property down here that if x is not equal to 0, then the inner product of x with x is positive. That's not automatically true for any symmetric bilinear form. All right. If you doubt me, for example, if I was to take, say, g of t comma x equal to, oh, I don't know, minus t squared plus x squared, then, oh my, rats. Sorry, that's not what I want. G of x comma y equal to minus x1 y1 plus x2 y2. So if that would define a symmetric bilinear form, but if you look at g of xx, what do you get? Right? Does that have to be positive if x is non-zero? It does not, right? In fact, this has really weird behavior. Like, notice that, if you put x equals to 1, 1, then g of xx is equal to 0, despite x not equal to 0, So this is not an example of an inner product by any stretch of the imagination. This is an example of something that's not an inner product, and yet is a symmetric bilinear form. All right? Okay, so moving on here. One of the first things I should point out, proposition is that if we were to take the inner product of a sum, I equals 1 to n, of a sub I, v sub I, with y, what can we do? Well, we can pull out the sum, all right? We can pull out the constants, and we can just do like this, right? So linearity in the first component of the inner product naturally extends to finite sums, all right? If you can do it for 2 and you can do it for one constant, you can do it for many. The proof of the proposition is induction. All right? So let me show you some examples. Number 1, I would suppose, is v is equal to Rn with the inner product of x and y simply defined to be the dot product of x and y, right? This is an inner product. This is, in fact, what the definition of inner product is really based on, is just trying to abstract this idea. Okay? Number 2, if we have v equals to, say, n complex numbers, complex n vectors, then we can give that the standard inner product x with y is equal to, I'm going to write a summation here. The sum, I equals 1 to n of x sub I, y bar sub I. So it becomes important for us to distinguish between stars and bars at this point. I sometimes inadvertently use star for complex conjugation before this point. I must cease and desist this practice. Because in chapter 6 of our textbook, Inzel, Spence, and Friedberg, there is a technical distinction made between bars and stars. Star means something more interesting than bar. So technically in our textbook, star is what I would call the Hermitian conjugate, whereas the bar is going to be complex conjugation. All right. Just to make this like a little bit more concrete for you guys, if we're in, for example, complex 2 space, if we had, oh, I don't know, like 1 comma I, and we're taking the inner product of that with, 3I comma 2 plus I, how would that go? We do 1 times 3I complex conjugate plus I times 2 plus I complex conjugate. Right? x1, y1 bar plus x2, y2 bar, which is explicitly and uninterestingly minus 3I plus I times 2 minus I, also known as 1 minus I. There you go. So the inner product of two complex 2 vectors could be a complex number, and I have zero intuition for what that means, but there it is. All right? Nevertheless, that is an inner product. You can check the axioms. Another example is this is kind of a meta example, but we could take V paired with the inner product this and exchange for, let's say, we can define inner product sub R like this as follows. We can just say the inner product of x and y sub R is R times inner product x and y, provided R is some positive scalar. So you could just take all of your inner products and rescale them. You could just rescale the inner products like this if you wanted to. And this would give you a new inner product space for that given vector space. It would be, as long as R is not equal to 1, this is a different inner product, and yet it has the same set of points, all right? So an inner product space is the point set paired with the notion of inner product, all right? Another important example, which is, now this one starts to get a little bit weird, but don't worry, it's going to be okay. Which is if we take V equal to C01. And so what that is F mapping from, say, 0, 1 to the reals, F continuous. All right, so the continuous functions with domain 0 to 1. In this case, we can define inner product, the inner product of F and G, we can make it equal to the integral from 0 to 1 of f of t, g of t, dt. Right? Now, I have not belabored the details of why these are inner products, partly because I'm coveting them for possible future homework problems. And also just because they're not that interesting, those proofs, like those are easy. This one maybe requires a little bit more work, not too much. Can you guys see why it's linear? What if I put, say F1 plus F2 there? What do you get? Right? But what do we know about the integral? It has that linearity property, right? I'm not sure that this is that interesting either, but I wrote it. So I'm this far in, I'm finishing it. F1 comma G plus F2 comma G. All right, so I guess that's not that interesting. And the fact that you can pull a constant out is pretty apparent from the properties of definite integration, right? What's perhaps a little bit more interesting is how does axiom, axiom C is kind of dumb here. It's clearly symmetric, right? Because we're just talking about multiplication of real valued functions, right? So that commutes. So it's pretty clear that this is equal to GF, right? I think the axiom, which is at least a little bit interesting here, is part D, right? Why is it that if the function is not equal to 0, then the inner product of the function with itself is necessarily not necessarily positive. There's a little bit of analysis to talk about there, right? So let's talk about it. If we have a continuous function, right? If f is an element of C0, 1, and f is not identically 0. So this means not identically 0. That means that there exists at least one point, right? So there exists p in 0, 1, right? Such that what? F of p is not equal to 0, right? So what happens when I do the integral? I do the inner product of f with f, right? That's the integral from 0 to 1 of f of t times f of t, which is f of t squared dt. So if f is continuous, did you know? If f is continuous, then there has to exist some, delta around the p such that f is non-zero everywhere near, like on that whole interval. See, I don't know where if f of p is like here, if this is p, then it can't be, say this is 0 and this is 1, right? It cannot be the case that it goes to 0. I mean, you can, let me say it this way. You can choose a delta, right? Such that between p plus delta and p minus delta, you have, f of x greater than 0, if it's greater than 0. And if it was less than 0, you could do the same by continuity. So what happens then when you integrate the square of something like this? So you've necessarily got a whole range of things which are either non-zero. Well, it's either plus squared or it's minus squared. Either way, you're adding together something that's squared over some finite, 2 delta interval, right? And there's nothing that can cancel out here, right? These are all positive. So if you're getting a positive contribution from that delta neighborhood, therefore this is, greater than 0. If this were a real analysis class, we could make that a little bit more precise, right? But that is enough for here. Yeah. But the continuity is key, right? If you didn't have continuous functions, then, well, anyway. If I chase that rabbit too far, we'll be driven to a discussion of measure theory, which is not what we're after in here. Okay, so definition. A m by n complex matrix, then the conjugate transpose which I believe we could also call the Hermitian conjugate. So in physics, the notation A dagger is used for this. All right, but here we'll follow the book, and he uses A star. And A star ij is equal to A bar of ji. So like here, A star is going to be an element of C n by m. So the conjugate transpose. I'm introducing that so that we can make sense of our next example. So continuing with my examples, example 5, if we have A and B in Cn by n, then the inner product of A and B, the standard inner product, is called the Frobenius inner product, and it's simply the trace of A B star. you can easily check that this has the requisite properties. Well, it's not entirely easy, I guess, but so like if we were in if you know, maybe 6 here, if A and B are in Rn by n, what would you do then? You just do AB transpose, all right? Now, this formula, when you actually work this out, what this works out to, guys, is like A1, 1, B1, 1 conjugate plus dot, 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 plus ANN, BNN conjugate. And literally all of the products between there and there. So it literally thinks of the matrix as an n squared vector strung out and just essentially takes the complex dot product of the matrix with itself as a n squared complex vector. I can prove this formula to you if you'd like. Let me see if I have time for such frivolity. All right, I'll probably regret this, but here we go. So if we have A with B is the trace of A B conjugate transpose, it's the sum I equals 1 to n of A B conjugate transpose II. But that is the sum I equals 1 to n of the sum J equals 1 to n of AII B conjugate transpose. Did I say II? I meant IJ. IJ, JI. But that is, let's just combine our I and J sums here. Sum over I and J going from 1 to n of AIJ BIJ conjugate transpose, which is what I said. Because that's exactly the dot product of the matrix with itself, thinking of it as a vector. You know, you're multiplying the IJ component with the IJ component complex conjugated here. All right. The next example, it does require a little bit of perhaps something you might not be totally comfortable with yet, but I hope it won't be too much. I don't think it's going to be too much. I need to define, so here's definition. If f equals to say f1 plus if2 is a mapping from the reals to the complexes where, you know, f1 and f2 are actually mappings from the reals to the reals, all right? So in other words, f1 and f2 are the real and imaginary component functions of f. Then how do we do calculus on such things? Well, df dt is by definition df1 dt plus I df2 dt, and like the integral of f dt is going to be equal to the integral of f1 dt plus I times the integral of f2 dt. So all I'm defining here is the calculus of a complex valued function of a real variable. This is nothing more than like calculus 3 with a complex notation. It's really nothing that you haven't seen before. If we differentiate a vector, we differentiate each component separately. If we integrate a vector, we integrate each component separately. That's all there is here. All right. But we need this to understand the following example, which your book calls H, and I will as well. So the H example. And H here is equal to, well, I would call it continuous functions from 0, 1 to the complexes, all right? So specifically, it's f from 0, 1 to the complex numbers such that f continuous, all right? In this context, we've got a complex vector space, all right? You can prove this is a complex vector space because the sum of continuous functions is, again, once more continuous. The scalar multiple of a continuous function is once more continuous. And I do mean scalar in the complex sense. So it is an honest to goodness complex vector space. And we can define the inner product in this context as simply the integral. Oops, my bad. Oh, just a second. I messed it up. Actually, we do 0 to 2 pi here. I forgot. We've got our reasons. 0 to 2 pi, my bad, 2 pi. And we're going to weirdly divide by 2 pi here. Integral from 0 to 2 pi, f of t, g of t, dt. This defines an inner product on H. Almost. What's wrong with it? How do I need to fix the formula? What's off?
Complex conjugate?
I need a complex conjugate right about here. Correct. That's right. So those are the examples that we'll be working with. So let me finally circle back and add to our proposition some additional properties that follow from our axioms. All right. So here they are. So I'll call this a theorem. All right, so for V, comma, inner product, a inner product space, if x, y, and z are in the space and c is a scalar, I'll use f this time. Is that better? Yeah, okay, all right. Then, if that's the deal, then guess what? We can prove linearity in the second spot. We do, in fact, have additivity. I shouldn't say linearity. We have additivity in the second spot. Break up sums like that. But we don't have quite linearity in general. What we do get is this. All right. So we pull a constant out of the second slot, we get complex conjugate, generally. C, the inner product of x and 0 is equal to the inner product of 0 and x, which is 0. D, the inner product with x and x is equal to 0 if and only if x is equal to 0. And then E is a kind of cancellation property. If we have the inner product of x with y is equal to the inner product of x with z for all x and v, I guess my quantifiers, this quantifier statement stops right here, right? Okay. Yeah. Like this business applies right to here, and then this. I guess it's, oh, whatever. Let me shut up. No one cares. If this is true for all x and v, then you can say y equals to z. So it's sort of a cancellation property. All right. These are all relatively easy to prove. I do have something non-trivial to prove today, so I want to make sure I leave myself enough time for that. Oh, we're okay. We're okay. So let's prove part A. So I'll show you a trick. if we have x with y plus z, we can rewrite that as x, y plus z, complex conjugate of the complex conjugate. Right? If you take the complex conjugate twice, you get right back where you started, so this is an identity. But then I can use the inside complex conjugate to trade that for y plus z, comma x, complex conjugate. Then I can use axiom A to exploit the additivity in the first slot. At this point, I need to know that the complex conjugate is itself additive, which is simple to prove. Ask anybody who's taken my complex. They've done it. In homework, right? Or did I not make that a homework? I'm not giving you guys enough homework in complex. I need to fix this. I missed a homework problem, right? No? Oh, you're not in complex. Never mind. I keep putting you back in complex. I don't know what's wrong with me. You're not in complex right now, are you? Okay, just checking. I told myself that you were in complex like in the first week of this class, and it's like burned into my brain. It's incorrect, but it's still in there. There's just so many students, it's hard to remember who's actually in the class.
Yeah, I was about to say.
Anyway, so there you go. I'll tell you what, I'll prove part D for you as well. And then we'll stop with these. Suppose, like, check this out. So if we have, I'm in part C, I'm going to leave D to you guys. C, if I take x with 0, right? I can rewrite that as x comma 0 plus 0, right? Because 0 is equal to 0 plus 0. But then by part A, which we just proved, this is x comma 0 plus x comma 0. This is pretty much the standard trick we always do to prove stuff is 0 in linear. This is the same thing we do to prove that the 0 maps to 0 for a linear transformation, right? Like t of 0 is t of 0 plus 0, so it's t of 0 plus t of 0, therefore t of 0 is 0, yay! Anyway, so that's equal to that, therefore x comma 0 is equal to 0. And once you know that, you also know that 0 comma x complex conjugate is equal to x comma 0, which is equal to 0, which implies that 0x is equal to 0, taking the complex conjugate of that equation. Okay, we got it. Let us move along. So, from every inner product, we can define a notion of vector length. All right? And that is called norm, or simply length. The length of a vector, or the norm of a vector, in an inner product space, we can define using the inner product. And here's how it goes. So definition, given inner product space V with inner product Langle-Ringle, define norm, a mapping from V to the reals by, did I say reals? Well, I think it is. Well, yeah, it has to be reals by the norm of x is equal to the square root of inner product of x with x for each x in V. This is a reasonable definition because we know that the inner product of x with itself is a positive real number. As such, we can take the square root of it and still get a positive real number, right? Well, not non-negative at least. It could be 0. Square root of 0 is 0. That doesn't cause us problems, right? So this, this right here is the length or norm of x. All right. So if you go back to all my examples, you can define the length of a vector, a real vector, a complex vector, the length of a matrix, the length of a function, the length of a complex function for h, right? So examples. So for Rn, the length of x is the square root of x dot x. For Cn, the length of x is equal to the square root of, I'll just use this notation, but if we wanted to, we could also rewrite that as the square root of x conjugate transpose x, I believe. For our n by n, the length of A is equal to the square root of the trace of AA transpose. This is also called the Frobenius norm. Just like the inner product was called the Frobenius product. I think I failed to say that today up till now. Sorry. Perhaps more interestingly, though, right, is on H, the length of the complex function would be, the square root of 1 over 2 pi, the integral from 0 to 2 pi of f of t times f conjugate, complex conjugate of t dt, right? Which you could write in terms of the modulus of complex numbers. You could write that as 1 over 2 pi, the integral from 0 to 2 pi, complex, the modulus squared of f dt. So if you guys don't know, if we have z is equal to x plus iy, complex conjugate, I've been assuming you guys know what that is. I hope you do. If you don't, here's what it is. The modulus of z is the square root of x squared plus y squared. It could also be written as the square root of zz bar, if you like. So these are some important formulas. This is also called the modulus of z, which is really the length of z as a complex number. So anyway, this, I should also mention, this norm that I just wrote down is usually called the induced norm. It is the norm that is induced by the inner product. If I had a different inner product, I would induce a different norm, right? Now, properties of the norm. So, short theorem here. The norm of Cx is equal to the magnitude of C times the norm of x. The norm of x is greater than or equal to 0. The norm of x is equal to 0 if and only if x is equal to 0. And the absolute value of the norm, the absolute value of the, oh good grief, the absolute value of the inner product of x and y is less than or equal to the product of the lengths of x and y. This has a name. This is the Cauchy-Schwarz inequality. And finally, the triangle inequality. The norm of x plus y is less than or equal to the norm of x plus the norm of y. So these are the properties of the induced norm, and those also happen to be the axioms of a norm in the abstract. To define a norm on a vector space is to give a function from the vectors to the non-negative real numbers which satisfies those rules right there, the triangle inequality. Oh, excuse me, the Cauchy-Schwarz inequality. It relates the inner product and the norm. That's special to the induced norm. So the theorem I just wrote up there in the corner, it's pretty easy to prove most of it, but the Cauchy-Schwarz inequality is actually quite tricky if you don't do what I'm about to do just now. So you want to definitely study the proof I'm going to give you right here, because I have assigned this to pretty intelligent students before to prove, you know, without this, and they got nowhere for a long time. So, yeah. So here's the proof. We're going to look at the proof of, here's what we're trying to prove. The magnitude of xy is less than or equal to norm of x, norm of y. All right. And so the proof, the book starts out by pointing out that if y is equal to 0, it's obviously true. Do you guys agree? If y equals to 0, it's clear that the identity holds. So if y equals to 0, then, you know, x comma 0 equals to 0, and, you know, the norm of 0 is equal to 0, so it works. 0 equals to 0, we're done. All right. Assuming that you proved the other part of it, right? Yeah? That the norm of 0 is 0. Okay, great. So suppose that y is not equal to 0. All right? And let's look at an identity. So 0 is less than or equal to the norm of x minus cy with x minus cy. Do you guys agree or disagree? Yes, for any constant scalar, this has to be true. Why does this have to be true? This is baked into the cake of the inner product, right? If x is not equal to 0, then the inner product with x and x is it's a vector with itself. So this is, you know, well, I guess I need the theorem I just erased that had 0. That gave me the 0 here. The positive is from the axiom. Okay. But now we can use the properties of the inner product to expand this thing, right? This is equal to, well, we've got x with x. Well, I'll do it in 2 steps. So x with x minus c y minus c times y with x minus cy. I'll do it in 2 steps. So there I used additivity of the first component. Next, I'll use additivity of the second component. So this is x with x minus c conjugate x with y minus c y with x plus c bar y with y. All right. Now I need a little bit, I'm going to rewrite this just a bit. Oh, okay. Yeah. Sorry, I was getting ahead of myself in the proof and thinking we were at another step, but we're not there yet. Okay, great. Fine. Now the next step is trivial, but also kind of a non sequitur. Like, this makes the proof very easy, but understand what's happening right now is a dirty trick. Let C equal to the inner product of x and y divided by the inner product of y and y. All right. Notice that C bar times xy is equal to the complex conjugate of xy divided by, yy times xy. Notice that C times yx is also equal to xy over yy times the complex conjugate of x and y by axiom C. I switched the order of x and y to get the complex conjugate there. And notice also that C bar of with yy is equal to xy with complex conjugate of xy divided by yy. Because the yy, there's two of them, they cancel. So what does this mean? It means that all the last three terms here, this one, and this one, and this one, they're all working out to the same thing. But notice that that means that this and that cancel, all right, because I've got a plus and I got a minus. And what then that gives me is 0 is less than, what is this? Well, this is by definition the length of x squared minus this term, which again, it's the first one, right? So this is actually xy times xy conjugate divided by the length of y squared. That's what this is. But by the way, that is straight up equal to the length of x squared minus the modulus of xy squared, because a complex number times its conjugate is the modulus squared of the complex number. Right? Which then gives me that the modulus of xy squared is less than or equal to the modulus of x squared times the modulus of y squared. Solving the inequality for the modulus term there, which then tells me that the absolute value of x with y is less than or equal to the modulus of x times the modulus of y. That's the Cauchy-Schwarz inequality. This is a pretty slick proof for it. I don't think you'll find a slicker one. I have proofs for this in the real case that involve like picky geometry involving unit vectors and things. So anyway, all right, so once you have that, proving the triangle inequality is actually pretty easy. So like if we, let's see here, I'll do it over here. The triangle inequality. If we look at the, so we'll do the triangle inequality and then we'll be done for today. Once I get through that short calculation. So continuing, if we look at the norm of x plus y squared, that is x plus y, right? But expanding out just like we did in the previous part of the proof, this gives us four terms, right? You got xx plus xy plus y with x plus y with y. Now the outside ones are exactly the inner product of x squared, all right? And then in the middle here, we've got xy plus xy conjugate, and then here's norm of y squared. Fun fact, if you have z is equal to a plus ib, then a is equal to 1/2 of z plus z conjugate. See this right here? So usually we call a the real part of z. A is the real part of z. So this idea down to here, we've got the norm of x squared plus twice the real part of the inner product of x and y. Like that. But guess what? The real part of any complex number is less than or equal to its modulus. So this is less than or equal to the modulus of x squared plus twice the absolute value of xy. Its modulus is a complex number, which then, by the Cauchy-Schwarz inequality, is less than the product of the lengths of x and y times 2. And then we factor. So if you got this squared is less than or equal to that squared, and these are both positive quantities, this implies then that the norm of x plus y is less than or equal to norm of x plus the norm of y. And that is the triangle inequality. So if we know that, yeah?
Do you need the triangle inequality to show that the real value in a complex number is less than the modulus?
That is the triangle inequality of real numbers. I'm talking about the triangle inequality for a norm on the induced norm of a vector space. But yes, you're right. It does, at the base of everything, depend on the ordinary triangle inequality for real numbers. You're absolutely right. Like, the modulus of z is the square root of the real part of z squared plus the imaginary part of z squared. And so I did use that, right, to say, okay, so the modulus of z is, greater than or equal to the absolute value of the real part of z. Well, you don't need absolute value here. If it's negative, that's still true. That I replaced this with its modulus right there. So, but you're absolutely right. Yeah, I did that. I've covered almost all of 6.1 today. I just missed one definition at the end on orthogonal space and orthonormal space, but that actually fits better with the next lecture anyway, so I'm content with it. And thank you for your quiz 4. I'll try to get those graded back to you Wednesday so that you guys have, the most time you possibly can have before the test. I do plan to teach Wednesday. If you don't want to be here because, you need to tailgate or whatever, I'd say I understand, but it's not true.